if you're confident with percentages and exponential models, then this question is something you could get right just by thinking about it and using logic, and the answer might seem obvious to you. But I have a feeling that if you got this wrong, that's exactly how you felt about your answer, that you thought that you had it right and felt pretty confident in it. And that's just a warning, right? I mean, we're in the difficult part of the test here. Our instincts are not to be trusted. Sometimes they will be right, but the percentage of the times they're going to be wrong is much higher than it would have been earlier in the test. And so the better, smarter way to handle this is to not trust your instincts and to, on every question, really try to have some sort of proof that you are correct. And with something like this, it's hard because it seems like we have to read this story and develop the equation. But no, because we don't need to think abstractly about math here. We are told a certain situation, and we can make up some numbers to just kind of see what would happen, right? So in planning maintenance for a city's infrastructure, a civil engineer estimates that starting from the present, the population of the city will decrease by 10% every 20 years. If the present population of the city is 50,000, what's going to happen T years from now? So let's just do what they're saying, right? In 20 years, you're going to have a decrease of 10%. So let's just say, okay, 20 years from now, when T is 20, the percentage is going to go from 50,000 to what? Well, we could probably do this in our head, but we have the calculator. So 10% of 50,000, we're going to multiply by 0.10. And so 50, 1, 2, 3 zeros, times 0.10 is 5,000. We knew that. And that's a decrease, so then I'll take my 50,000 and subtract the 5,000, and that tells me 45,000 is supposed to be the new population. So that's the result that I would like to get out of these equations when I plug in 20 for t. So basically what I've done here is I'm supposed to have a whole equation that represents all the possible values of t and everything in between. But that's hard for my brain to comprehend, so what I've done is I've arithmetized by thinking of one instance, one point on these graphs that represents the story that they're telling. And I picked the easiest point, right? Because they said every 20 years this is going to happen, so I stuck with a 20-year interval, right? It's just easier to think about. So now we take our value of t and we're going to plug that in to the t's and all the answer choices and see which one gives us 45,000. So we have our calculators. This is not a big deal. So choice A is 50,000 times 0.1 times 20 times 20. Well, that's going to be a big exponent. So 20 times 20 is 400. 0.1 to the 400. Ooh. My calculator thinks it's 0 because it's going to be such a small number. So the point is, it's not going to work. It's too small of a number for my calculator to even handle, and so no good. Let's keep going. Let's change color to make it easier to see. 50,000 times 0.1. Now we've got 20 divided by 20. So 20 divided by 20 is 1. So now this is just 0.1 times 50,000, which coincidentally is the same math that we did before when we were solving this without the equations, right? 0.1 times 50,000. So it's 5,000. So you could see how someone might pick choice B. It kind of it incorporates some of the logic of the question. And so it's a trick, it's a trap, but it shows that maybe there's something to that choice. But let's keep going. Let's look for one that actually gives us what we want. 50,000 times 0.9, 20 times 20. So again, that's 400. So 0.9 to the 400. I think this might break my calculator too. Yeah, it's small. It's a really, really small number. It's still going to be written, though, in scientific notation. So my calculator is okay with it. And so 2.49 times 10 to the minus 14. Those are a really tiny number if you remember how scientific notation works. So it's probably D, but let's just be safe, right? So 50,000 times 0.9 to the 20 divided by 20. So again, 20 divided by 20 is 1. So 0.9 to the first is just 0.9. And so 50,000 times 0.9 is 45,000, what I expected. And so there's my proof, hard proof, that D is correct. The reason that this ends up working is basically if we're decreasing by 10%, we really have 90% left. So this is a very frustrating way that we talk about percentages versus how we actually do the math. So let me just give you an example. If you go to a store and you have a coupon for, in this case, let's say 10% off, right? A 10% decrease in the price. If you go to the store and you're buying, a $100 calculator, then you give them a 10% off coupon. It's not like you're paying $10. You're not paying 10% of the price. You're paying 90% of the price. So we're taking 10% and we're subtracting it away, but there's 90% left. And so the way we talk about discounts and decreases is we say things like a 10% decrease, 10% off. But mathematically, what we really mean is 90% on, right? So 10% off is really 90% on. And in our formulas, 90% is going to be what shows up. And so I've used what I call the open formula on some other percentages questions. So you might be familiar with that, and that will take into account this kind of discrepancy. But for now, just if you're confused on this question or you feel like you're kind of reasoning it out, then a safe way to prevent a mistake is to just use numbers and let your reasoning see itself in action, right? See the numbers change. And hopefully that, if you were going to make a careless mistake, it prevents it and saves you 10 points. And, I think arithmetize really does come in handy on the question like this because I don't trust myself, but I do trust the numbers.